Good morning, students. Is my voice audible? Students, is my voice audible?
Yes, sir.
Okay, so in previous classes, we have completed first module. Today, I will start second module. Second module title is Resistive Sensors. So in this module, we will see different types of sensors, and all the sensors use resistance. Okay, so in these resistance, in these sensors, we use resistance to estimate the physical parameters. Sensors based on the variation of the electric resistance of a device are very common. That is because many physical quantities affect the electric resistance of a material. Thus, resistive sensors are used to solve many measurement problems. Temperature dependent resistors can also compensate for thermal interference in systems measuring other quantities. The different resistive sensors are classified by the physical quantity being measured as mechanical, thermal, magnetic, optical, and chemical variables. The different resistive sensors are classified by the physical quantity being measured as mechanical, thermal, magnetic, optical, and chemical variables. First sensor in resistive type sensors is potentiometer. So potentiometer is a resistive device with linear or rotary sliding contact. So here we have linear potentiometer. Potentiometer is a resistive device with linear or rotary sliding contact. The resistance between that contact and the bottom terminal is here we have R is equal to rho by A into X, and we can elaborate expression as rho L by A, where R is the resistivity, that is rho. Rho is the resistivity and A is the cross section, L is the length, and X is the distance traveled from the bottom terminal, and A is the corresponding length fraction. Here, this wiper has moved from bottom to top. So here wiper has taken this position, so distance traveled, the displacement is X. Figure B shows a symbol and figure C shows a symbol for rheostat. See students, potentiometer and rheostat works on same principle, but the physical dimensions are different. I will show you the images now. Potentiometer and rheostat. See students, here we have linear potentiometers in different sizes. Depending on the position of the wiper, resistance will vary. This is a linear potentiometer. And next, this is rheostat. Are you able to see rheostat, students? Or still potentiometer is appearing on the screen?
Rheostat, sir.
Okay, right. So this is called rheostat. Rheostat and potentiometer works on same principle, but sizes are different. And this is rotary potentiometer. This is our wiper. Internally, we have to rotate this. If you rotate this, resistance will vary. Potentiometer is a zero order system. Students, in previous module, we have seen different types of systems. Zero order system, first order system, and second order system. Although it can be itself a component of a non-zero order sensor. Most of the limitations are outweighed by the advantages of this device. It is simple and robust and yields a high level voltage with high accuracy relative to its cost. Dual potentiometers operated by a single control stick move in 4 quadrants to locate a point in a plane. Students, here we have joystick type of potentiometer. In this we have 2 wipers. We can move joystick and left and right, and we can move joystick and top and bottom. Depending on the position of the joystick, we will get different resistance values. Dual potentiometers operated by a single control stick joystick move in 4 quadrants to locate a point in a plane. Movement along the x-axis controls Rx and movement along the y-axis controls Ry if both potentiometers are supplied by the same voltage. So here you can see both resistors are supplied with the voltage VR. This is called joystick based on a dual potentiometer operated by a single control stick. Students, here we have specifications of linear and rotary potentiometers. First column shows linear potentiometer specification. Second column shows rotary potentiometers. Input range 2 mm to 8 meters. That is the range of the potentiometer. We can move least displacement as 2 mm and we can move higher displacement as 8 meters. And in rotary potentiometer 10 degrees to 60 turns. Linearity 0.002% to 0.1%. And resolution 50 micrometers. All these parameters, static characteristics, we have seen in previous module, students. So go through the table for 2 minutes, then we will see another details of the potentiometer. Potentiometers based on a carbon film, sometimes mixed with a plastic deposited on a form, and a noble metal alloy wiper with multiple contacts yield high resolution and long life at a moderate cost. Students, if we paste our resistance on carbon film, it becomes chemical type of potentiometer, but they have high temperature coefficient. So in the potentiometer, if you move wiper, then only we should get change in resistance. But in chemical based potentiometers, depending on the temperature also, we will get change in resistance. In yesterday's experiment RTD, we have seen if temperature increases, RTD resistance is increasing. So here also, depending on the temperature, it will give variations in the resistance. Other models use a thick film configuration consisting of silver filled polymetric ink. Precious metal contacts yield the best electrical and live performance at a higher cost. For high power dissipation and high resolution, the resistive element of cermet. Cermet is one kind of ceramic material, students. The resistive element of cermet models is based on particles of a precious metals fused in a ceramic base and deposited by the thick film techniques. So in previous module, we have seen thin film and thick film technology. So here we are using those technologies to implement a potentiometer. Hybrid potentiometers use a wire wound core coated by a conductive plastic. The conductive plastic confers smoothness but limits the power rating. So all these points gives us information about the construction of the chemical-based potentiometers. Electrolytic or liquid potentiometers have a particular arrangement intended for tilt measurement. There is a hermit curved while partial filled with conductive liquid and 3 metal electrodes contacting the fluid, a large central electrode and 2 shorter electrodes, one at each side, that is A is equal to 0.5 volts and 12.2 5 volts. AC voltage with 20 Hz to 20 kHz is applied to the other outer electrode. So here we have the chemical based potentiometer. When the tube is horizontal, the electric resistance from the central electrode to each outer electrode is equal and the voltage at the central electrode is half of the applied voltage. So when the pipe is horizontal, as a tube tilts, the air pocket shifts, the current path between outer electrodes changes, and so does the resistance between the central electrode and each outer electrode. The output voltage is proportional to the tilt angle. The output voltage is proportional to the tilt angle. So here we have liquid potentiometer. Figure A and figure B shows tilt sensors, but principle is different. When the tube is horizontal, the electric resistance from the central electrode to each outer electrode is equal and the voltage at the central electrode is half of the applied voltage. As the tube tilts, the air pocket shifts, the current path between outer electrodes changes, and so does the resistance between the central electrode and each outer electrode. The output voltage is proportional to the tilt angle here. The output voltage is proportional to the tilt angle. And the second one, a rolling ball acts as wiper. A rolling ball acts as wiper in pendulum, changing the resistance between, so here we have ball, changing the resistance between the resistor ends and a conductor supported by a vertical plate. So here this ball will rotate, and because of that rotation we will get change in the resistance. Response time ranges from 100 milliseconds to several minutes. Temperature interferes because it changes the resistivity of the electrolyte. Tilt switches use two closed electrodes and a mercury that closes the circuit when the wire rotates by a given angle. So here you can see, if you move this pipe, or if you tilt this pipe, we will get variation in the resistance. Figure 2.3b shows another potentiometer intended for inclination measurement. A vertical planar substrate supports a concentric conductor and resistor. This one, pendulum based potentiometer. A conductive ball is pressed against the resistor by a channeled housing ring and acts as a wiper. Here, this is our rotating ball. When the housing tilts, the ball rolls on the lowest point and changes the resistance between the conductor and the resistor terminals. Here we have resistor and here we have conductor. See students, here we have potentiometer, and we are using this potentiometer to sense the level in a liquid. Here we are using this potentiometer to sense the level in a liquid. And this is another type of resistor. Figure 2.4 shows a level sensor with a response with no wiper. We observe here there is no wiper because liquid will act as a wiper. There is a stainless steel base strip with a gold contact strip on one side. A gold plated nichrome wire is preciously wound to form a resistance helix. When the tape is immersed in liquid, hydrostatic pressure makes the helix wire contacts gold contact. See, here we have contact. The resistance gradient is about 10 watts per centimeters. Force sensitive resistors are conductive polymer film sensors whose conductance is roughly proportional to the applied force, and the application point behaves as virtual pressure sensitive wiper. Because of the liquid, this resistance will contact the gold plate. So then we can use this for measurement of pressure also. Figure 2.4b shows FSR-TM sensor interlink that consists of two polymer films. Here we have two polymer films. If you make this first plate to contact with the second plate, we will get a different resistance. One film is doped by a covalent agents that are rendered surface conductive. The other film has printed interdigitated electrodes facing the conductive surface of the adjacent film. Contact of the two films makes the conductive surface short electrode fingers, thus reducing the electric resistance between end terminal. So here you can observe, but if you allow this first plate to contact with the second plate, we will get contact in between the first plate and second plate chemicals. Then we will get different resistance values. And here we have another type of potentiometer. Sensing cable to detect liquid hydrocarbons. The conductive polymer swells when hydrocarbons diffuse into it. Starting two sensing wires, the equivalent circuit shows that the lead behaves the virtual wiper. Here you can observe. We don't have contact here, and here we have contact because of the hydrocarbons. Figure 2.5 shows a hydrocarbon sensor equivalent to a potentiometer. Based on the swelling of polymers when exposed to solvents and fuels, there is a cable consisting of an outer porous contaminant braid, a conductive polymer sleeve, an inner separator braid, a sense wire, and an inner wire. So these are the different parts of the sensor. A conductive polymer, the cable is buried in the monitored area. The cable is buried in the monitored area. Liquid hydrocarbons penetrate the braid and diffuse into conductive polymer sleeve that swells inwardly. So this figure shows swollen state, and here we have dry state. The conductive polymer then shorts the two sense wires together, and the resistance decreases below 20 kilowatts. This sensor has been proposed to detect and locate fuel leaks along buried pipes, tanks, and double contained pipes. There are also models sensitive to water, conductive liquids, and liquid organic solvents. So here we have sensor which can vary its resistance depending on the availability of the hydrocarbons. So once again, we will see potentiometer detailed strengths, then we can go to the strain gauge. So we have two types of potentiometers, linear potentiometer and rotary potentiometers. If you move the wiper, its resistance will vary. If you observe the circuit here, we are supplying voltage, and voltage source is connected to a resistor in series. So wiper contact will make changes in the resistance. And here we have symbol for potentiometer. And this is a symbol for rheostat. In this figure, wiper has moved up to X. The displacement of the wiper is X. This figure is the joystick type of potentiometer. We have connected two voltage sources and two resistors. And joystick we can move in two directions, left and right and top and bottom. Potentiometers based on a carbon film, sometimes mixed with plastic deposited on a form, and a noble metal alloy wiper with multiple contacts yield high resolution and long life at a moderate cost. But they have high temperature coefficient. Other models use a thick film configuration consisting of silver-filled polymetric ink. Precious metal contacts yield the best electrical and live performance at a higher cost. For high power dissipation and high resolution, the resistive element of ceramic models is based on particles of precious metals fused in a ceramic base and deposited by thick film techniques. Hybrid potentiometers use a wire-wound core coated by a conductive plastic. The conductive plastic confers smoothness but limits the power rating. And here we have potentiometers to find out the angle of inclination. First one is chemical based, that is liquid potentiometer, and second one is pendulum based rotating ball potentiometer. Response time ranges from 100 milliseconds to several minutes for the liquid potentiometers. And here we have two types of potentiometers. In figure A, we don't have wiper, but because of the liquid level, resistor will get contact with the circuit and its resistance will vary. So here we have two plates. If we allow to contact first plate with the second plate, then resistance will vary. And here we have sensing cable to detect hydrocarbons. So here we have sensing cable to find out the hydrocarbons. Strain is the next device is strain gauge. Strain is the amount of deformation of a body due to an applied force. Strain is the amount of deformation of a body due to an applied force. More specifically, strain is defined as the fractional change in length, as shown in figure below. Initially, this metal plate length is L, and we are applying strain on the plate. So if you observe, students, here we got a small increment in the length. And strain is represented by modulus. Strain can be positive or negative. Although dimensionless, strain is sometimes expressed in units such as inches per inches or mm per mm. In practice, the magnitude of measured strain is very small. Therefore, strain is often expressed as micro strains, micro modulus, which is modulus into 10 to the power of -6. So here we have a formula for the strain, delta L divided by L. Delta L divided by L. This is the formula for strain. When a bar is strained with a uniaxial force, as figure 1, a phenomenon known as Poisson's strain causes the girth of the bar due to contract in the transverse. If we are getting increment in the length, and we will get decrement in the width or perpendicular direction, the magnitude of this transverse contraction is a material property indicated by its Poisson's ratio. The Poisson's ratio eta of a material is defined as the negative ratio of the strain in the transverse direction, that is perpendicular to the applied force, to the strain in the axial direction. So here we can see the relation between the Poisson's ratio and the strain. And Poisson's ratio for steel ranges from 0.25 to 0.3 because both are same units. So no need of giving any units for this Poisson's ratio. So this is the details of the strain, students. Go through this slide, then we can see the details of the strain gauge. While there are several methods of measuring strain, the most common is with a strain gauge. A device whose electrical resistance varies in proportion to the amount of strain in the device. For example, the piezo-resistive strain gauge is a semiconductor device whose resistance varies non-linearly with strain. The most widely used gauge, however, is the bonded metallic strain gauge. The metallic strain gauge consists of a very fine wire, or more commonly metallic coil arranged in a pattern. This is the figure 2, and here you can see the strain gauge. Bonded metallic strain gauge. The metallic strain gauge consists of a very fine wire, or more commonly metallic coil arranged in a grid pattern. The grid pattern maximizes the amount of metallic wire or coil subject to strain in the parallel direction. The cross-sectional area of the grid is minimized to reduce the effect of shear strain and Poisson's strain. The grid is bonded to a thin backing called the carrier, which is attached directly to the test specimen. Therefore, the strain experienced by the test specimen is transferred directly to the strain gauge, which responds with a linear change in electrical resistance. Strain gauges are available commercially with nominal resistance values 30 to 3000 ohms, with 120 to 350 and 1000 ohms being the most common values. See here, students, we have a fine wire, and this is one kind of strain gauge, and the other one is we can frame coils as grid. The basic point is this should be a resistive material, and here we should have cables. These two cables we have to connect to a circuit, and then we have to apply force on this grid, force on this fine wire. Then we will get strain in this fine wire. When we are getting dimensional changes in this wire, we will get a change in resistance. That is the details of the metallic strain gauge here. And different ranges we have, that is 3000 ohms. Sorry. We have different resistance values for the strain gauges, 30 to 3000 ohms. And with the 120, 350 and 1000 ohms being most common values. And here we have details of the strain, and here we have details of the strain gauge. So go through this for 2 minutes, and we will see the types of the strain gauges. Here we have details of the bonded metal strain gauge. Go through this slide. And different types of strain gauges and details of those strain gauges we will see in next class, students. In this class, we have seen potentiometer and details introduction of the strain gauge and details of the strain gauge we will see in next class.